Very good afternoon to all of you, and welcome to the session on BERT and GPT. So we'll talk about BERT, bidirectional encoder representation from transformer. So if you see the keywords here are transformer and the bidirectional. So we'll talk about everything in detail. And as I mentioned that since the transformer is already done with you people, so I will not go in the details of the transformer model, but I'll discuss that what exactly BERT is and how is it different from the transformer model. So it clearly says the encoder representation from transformer. So whatever the complete transformer model you have, we are taking only a part of it, the encoder part of it. I request each one of you to please mute your mics and you can unmute whenever you have any question. So, so the previous work till now, what said was कि we had the sequential to sequence model, and then we said, okay, let's go for a neural machine translation. When we went to neural machine translation, then there was a need of an attention mechanism which can lead to a transformer model. So, and regarding the word embeddings, we started with word to vec. Then we went to a little more advancement on word to vec and went to Grove. Mo is another way to do the word embeddings. Then we come to GPT, and finally we came to BERT. So, when I say GPT, the GPT is not a process for word embeddings, but it is the decoder model of the transformer, and this is the encoder model of the transformer. So that is the basic difference between BERT and GPT models. By the end of this session you would be able to appreciate the difference between these two firstly, and we would also do the implementation of BERT. So this is the paper that I was talking about, Ashish sir, regarding the Vaswani paper, which talks about the attention mechanism in detail. So what exactly happens in the case of a sequence to sequence network is we give the input to the encoder, it gets decoded by the decoder, and then finally you get the output. So if you give x1 as the input, then you get y1 as the output. If you then again give x2 as the input, you get y2 as the output. So but that has to be done only once we have got the y1 as the output, then only the x2 can be given as an input. It has to be done in a sequential manner. So there are various, you can say, applications of such type of networks, sequence to sequence networks. One is a input language translation, summarization, dialogues, previous utterances to next utterances, then parsing, then code generation. So these are different NLP tasks that can be performed with the help of sequence to sequence nature of the network. But this has the ability to perform state of the art performance in many MNLP tasks. Actually, nowadays, we don't use RNN and LSTM much, as these are sequence to sequence models and they take a lot of time. We have already discussed, in fact, that LSTM is very, very slow. It gives you very good answers as compared to RNN, but it is very slow because it is trained on a huge set of parameters and it requires a lot of weights to be trained. Hence, it is very, very slow. So, but BERT is basically a pre-trained model. So it says it is a pre-trained model. So we don't have to spend much of the time in training it, and we don't need that much of computational power also to train the model. And it is a bidirectional representation. So this is a very important word which says bidirectional. In fact, LSTM was modified by some of the researchers to give you bi LSTM. So what is the meaning of bi LSTM is by LSTM, which said that, like in the case of the LSTM, when I say the same example which I gave you the last time I went to the market. So, what it was trying to do is it was trying to find out the relationship only in one direction, if you remember. So, when we said n-gram model, so we say I went to the market. So we were going only in the forward direction and we were trying to find out the relationships between I went to the, and so on. So this was an advanced version of Ngram's model, the LSTM part, which was which was trying to find out the relationship between the two different words. But by LSTM said that I will not go only in the forward direction, but I'll also go in the backward direction. So there should be a relationship between I went and went I also. Went to went to the to, like this. So if I'm going towards front, then I should go towards backward also. So suppose if I'm trying to access to, so I'll also do the analysis of I went and the market. So I went is something which is before two, and the market is something which is after two. So if I'm going for a bi-LSTM model, or especially the BERT model, it will take care in bi-directional way, both the directions, forward and backward. Okay. So by um, by jointly conditioning on both left and right context in all the layers, so it will try to figure out the context of the sentence, the reference to context in both the directions, the left and the right. So, to train a particular language model, there are two ways to do it. Either it goes for context free language, or it goes for a context sensitive language. So, if you remember, we talked about bag of words. So, bag of words was absolutely context free because it didn't care that what is the order of the words, and it was simply said that whether that word is present in the corpus or not. Then we went one step ahead and said that okay, let's have a relationship between the words also. But we are not exactly considering the context, but we are just finding out the relationship between the different words. So this was word to vec, which talked about the embeddings. And then we went to the contextual model, where we said that the sentence before the sentence that we are currently analyzing should also needs to be considered, which actually forms the context of the sentence. The context of the sentence is basically the sentence prior to the one which I am trying to analyze here. So that is the contextual model. So basically, BERT actually works with the BERT weights are learned in advance through two unsupervised tasks. Now, what are two unsupervised tasks? Which are masked language modeling, that is predicting a missing word given the left and the right context. So we have already said that BERT goes in the bidirectional manner. So if suppose I am considering the C word, then I need to consider the C minus 1 and C minus 2 words, C plus 1 and C plus 2 words. ठीक है ना? So if my window is 2, so two words before and two words after needs to be understood. Correct. So it says I am trying to train the model with respect to two things. First thing is masked language modeling. That is, I'm trying to predict a missing word. I'm trying to predict this word when the previous two words and and the next two words are given. And once this center word is done, then I also try to figure out the next sentence. So if you remember, when I was telling you about chat gpt, so we said that the chat gpt works in the way when it is trying to figure out the next word prediction. So it keeps on predicting the next word, next word, next word, and in this way it is able to predict the complete paragraph. The same concept is used here with two things. First is I want to predict the center word, and also I am doing a next sentence prediction instead of next word prediction. So in this case, I would be able to find out the temporal order of the sentences. That is, sentence 1 should come before sentence 2, and sentence 3 should come after sentence 2. So of course, BERT uses the transformer along with the attention mechanism in order to understand the contexts between the different words, and most importantly different sentences also. So multi-head attention is used in BERT. It uses multiple layers of attention and also incorporates multiple attention heads in every layer. So first and the foremost, I have very layers, and every layer will have many attention heads. This is what it is trying to say. And since the model weights are not shared between a layer, single BERT model effectively has up to 12 cross 12 different attention mechanisms. So it says I have 12 layers, for example, and every layer will have 12 heads. So I have 12 cross 12 attention mechanisms. I'll give you a minute to just go through the slide and understand the things well. Take a minute.
Madam, just relating one
Yes,
of the diagrams that we saw earlier in the morning to this one. Earlier, we had for a, not exactly for bird, in general, we had an encoder block and decoder block.
correct,
From, from encoder, we had Q and K, which were sent to this decoder block.
correct.
So, in case of bird, there is no decoder. So, all Q, K,
No,
V, everything is inside the encoder
encoder
only.
itself. Yes.
Okay.
So we have Q, K, V, just a query, key, and a value. So we have a set of query, key, value, which is done with the help of the encoder itself. Why don't we need a decoder? We'll talk about that in detail. Don't worry.
Okay. Great. Thank you.
So BERT basically, what does it learn? So how does BERT work? That we will talk about. So first and the foremost, it extracts all the tokens from the sentence. What are tokens? The simple the words, and it will also try to check it out whether that word is present in the dictionary or not. If the word is not present in the dictionary, then it would be an out of vocabulary word. Out of vocabulary word, that means it is not present in the dictionary, or it may happen that it is present in the dictionary but its form is not present in the dictionary. So it says if play is present, then it may happen that playing is not present. So I'll simply say ki play is there, and then different forms of the same word which are there in the which can be there in the vocabulary. So what we'll do is we'll try to, this is very similar to the lemmatization thing that we did last time, in which we say that play plus something ing, play plus ed. So basically what is this representing? It is representing, it is a subwords. So subwords, you can just say it to be as the suffix or the prefix here that adds to the current word, which forms the different form of the same word. So very similar to the morphology and the stemming part that we did. And when it wants to process any sentence, then it will add a cls at the beginning, and it will add SEP tags after every sentence. So SEP stands for the separator. So it will have a SEP token between the sequence and at the end of the sequence, and it will have a CLS classifier which will tell that okay, we are going to start a new sentence here. So we have the first is a contextual word representation. So it can use something very much related to glove or word to vec. Then it will talk about the mask language model, the next sentence prediction, and the model architecture. So if we are going for a non-neural word representations, then it would be simply saying that one hot encoder, or we are simply saying that the word is present in the corpus or not. So we can say simply with 0 or 1 like this. So either it is a non-neural word representation, or it is a word representation using neural networks, word to vec or glove. Or we may go for elmo or something like that for embedding. Once the embedding is done, then we can fine tune it with OpenAI GPT or BERT. So we'll talk about this. We are already aware, so I am skipping this part that we are giving a vector for every word. So it simply say building the magical vectors. Why do we call it as magical? Because when we give the vector for a particular word, then this vector is responsible to give you the context of the word. So this is a one hot vector that we talked about, but then it will not be able to find out the context. So we said that, okay, we'll have something different like this. And we have also seen the implementation of this in the code. We saw the vector of a particular word, and this is how it works. So basically, we went from text to one hot encoders. We said that one hot vectors are not very efficient, so we went to word embeddings, and we went more one step ahead, and we said that okay, let's start using the neural networks to do the word embeddings. So this is a contextual representation, and this is the n-gram model, if you remember, that we talked about. So if you say the deep bidirectional pre-training using the transformer blocks, learning the contextual representations with unlabeled data. Why we are saying unlabeled data? Because we said it is an unsupervised learning technique. So unsupervised will always have an unlabeled data. If it would have been labeled data, then it would have been very easy for us to do it. We already know that this word represents what. Yeah, what is the meaning of this word? But it is an unlabeled data, means that we don't know anything about the context of the word, and it is our responsibility to get the context. So it is just not the embeddings, but it is also being able to initialize the model with the help of these contexts. So pre-training is very powerful. That is, we need to pre-train the model well so that we are able to perform the tasks. So as one of the tasks we'll see as summarization or question answering. So if you just see here, at the very first instance, we used to have the feature based word embeddings. Then we did the fine tuning, and then we applied the GPT or the BERT model to it. So BERT model gives you the bidirectional embeddings through from the transformers. So so this is what a BERT is. So BERT will only have this encoder architecture. It will not have the decoder architecture. So as what sir was mentioning, that how we are able to do this when we don't have the decoder, so we have the q k v values done, how it is going to take care of this k q v values when we don't have the decoder part. Taken as if you see this entire thing is a transformer, and if you don't have this, it is a BERT model, because it is only concentrating on the encoder part of the system. Why do we need only the encoder? Like, for example, I'm talking about summarization. So I just need to encode the input. From encoding the input, I'll do some analysis on the encoded input and I'll get the answer. I don't have to decode the output also for it. That is why I need only the encoder model. So the word embeddings are the basis of the deep learning. So word embeddings can be done with any of these two methods. So word embeddings are applied in a context-free manner. Open a bank account on the river bank. So in this case, both the banks will have a similar word embeddings. So now if we try saying that, okay, let's have the contextual representations. That is when we are saying that this bank should be different from this bank. If I simply say word embeddings, then that will not solve my work. If suppose I say bank corresponds to point 1, point 2, point 2, 3. So the same bank used in different contexts will have a similar word embedding. But if we want to use the contextual representations, then in that case, I need to have a different embedding for the two different banks. The bank account should have a different embedding as compared to the river bank. Okay. So if you see here, this is what Elmo or Glove does. That is, it gives you an embedding which is as per the context. So this actually, the Elmo gives you the deep contextual word embeddings.
So, madam, the word bank will have multiple embeddings in that case because it will be
Yes, yes.
okay.
Depending upon the reference to context, it will have a different embedding. So if it is
Okay.
used as a bank account, so then it would be a different embedding. If it is used as a river bank, it will have a different embedding.
Oh, thank you.
So in fact, when I gave you the introduction, when I was telling you about the reference to context, this is where it is important. Depending upon the context, that 255 length vector would be assigned, or 512 length vector would be assigned. That will also contain the context of the word, whether it is being used as a bank account or it is being used as a river bank. So it says we train the separate left to right and right to left language models. LM is large language models. So I say open a bank. op- it would be able to do a left to right and right to left. So when I go from open a bank to open a bank,
Door opposite ಅಲ್ಲಿ ಯಾರಿಲ್ಲ
so I say open a bank to open a bank, and this was from left to right. And if I go from right to left, bank a open. Okay, so it is going in both the directions, so that is why we say bidirectional. BERT stands for bidirectional. I request each one of you to
Prescription
please
paper.
mute your mics.
Bill.
Please mute your mics. Okay,
പണ്ടോ ഓർഡർ സാധനത്തിന്റെ ഡെസ്പാച്ച് മെസ്സേജ് ഇപ്പോഴാണ് വരുന്നത്.
please mute your mics. So when we were said, what are the different steps which are involved in BERT? The first point was word embeddings. The second point is masked input. So the masked language model says, key, if suppose I have a complete word, the man went to the store to buy a gallon of milk. So the logic says mask 15% of the words. So this consisted of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it says 15% of the words in the in the sentence should be masked. And once they are masked, then I would try to find out what are those words and then predict the masked words. So why we are trying to do this is ki when we try to predict the masked words, then it becomes easy for us to understand the context of the sentence and to understand the meaning of the complete sentence. You can have this analogy that whenever you are trying to learn a concept, then mug up the concept, then you always ask your friend to, okay, you ask me again whether I am able to answer the question correctly or not. Like my son yesterday said ki mummy mujhse ye questions पूछ लो. So why did he do it? Because when I would ask the questions from him, then I would be able to train him on those questions. Correct? Because now he can give the answers without looking at the answers. So he is trying to test himself whether he is able to give me the correct answers or not. Correct? So you can relate this masked LM part very much to the same analogy in which we say that we test ourselves by giving the answers to the questions whom we which we have already learned. So we are just trying to test our knowledge ki whether whatever we have learned is correct or not. So we mask 15% of the words and then we try to predict those words. I cannot take too much of masking because then the model will become very expensive to train. Of course, yes, if suppose I say, you ask me all the questions, whatever I have learned, so then it is definitely going to take a lot of time and the wastage of time also. Because in that time, I may learn some extra things. Correct. Suppose I have learned 100 questions and there are 200 questions to be learned. So if I say that, okay, whatever 100 questions I have learned, you ask me those questions. So definitely it will take a lot of time for those 100 questions to be asked and then answered. It may happen that I won't be able to learn the extra 100 questions that was supposed to be learned. Correct. So similarly, if you say, so what exactly what we do is, we don't ask all the 100 questions, but we ask at random some 3 to 4 questions. So in this case, we are saying 15% of the questions. So 15 questions I'll ask at random. And if the person is able to answer those questions, so it proves that, okay, whatever you have learned is correct. That is, you have learned well. And if I ask only one question out of those 100, it may happen that I was able to answer that question. But there can be some other 2 3 questions which I was not able to answer. Yeah, which I may not able to answer. Okay, so taking very less masking is also wrong, and taking and a large amount of masking is also wrong. Correct. If there is too much of masking, then it may be very expensive to train. And if it is very less masking, then it is not enough to get the context. Too expensive, not enough context. So both the things needs to be avoided. So we keep ourselves generally usually to be 15%. Once we are able to predict the words from the mask, then we'll try to predict the next sentence. And this next sentence actually is with respect to the previous sentence, and you are able to have the relationship between the two sentences. The reference of the previous sentence is used to predict the next sentence. So the man went to the store was the first sentence, so probably he bought a gallon of milk because he went to the store. So generally he buys milk. So this time also he has bought a gallon of milk. The man went to the store. Penguins are flightless. Now these two sentences don't have any relationship amongst themselves. They are not at all related to each other. So I'll simply say not next sentence. So he bought a gallon of milk can be the next sentence of he went to the store. But penguins are flightless cannot be the next sentence for the man went to the store. Are you getting my point here? So first we said we do the word embeddings. Once we have done the word embeddings, then we do the masked language model. And once it was done, then we went for next sentence prediction. So the transformer encoder has the same thing as was we had the encoder part of the transformer architecture. We have the multi-headed, it is self-attention, forward layers, layer norm and residuals, and the positional embeddings. Why do we need positional embeddings? So that the positions of every word with respect to other words can be taken into account. Whether it is a second word, or it is a fourth word, or it is a third word, what are the 2 words before, what are the 2 words after, and so on. All this has been taken into account. So BERT we have already discussed is a multi-layer bidirectional transformer encoder. Why we say transformer encoder? Because it contains only the encoder part of the transformer. So when BERT was introduced, then 2 models of BERT were introduced, one with 12 layers and the other with 24 layers. So 12 transformer blocks, 12 attention heads. So 12 attention heads and 12 layers, 110 million parameters. 24 layers, 16 attention heads. So 340 million parameters. Okay. So we call it as BERT base and BERT large. Just take a minute here. Since you have already done the transformer model, so for example, whatever the example that we are looking at over here, we'll say the same example in the code as well. The little girl tears up everything she gets. She gets tears when she goes to school. So if you see here, this is the sentence which I have used. You can use any other sentence in which there is a confusion between a word. So if you see here, tears, these 2 tears should have different embeddings. That is what the concept we want to have. These 2 tears should have different embeddings, because here this tears means padana and this tears means asu. So the word embeddings of these 2 tiers should be absolutely different. because the word tears appears twice with two different meanings. One is destroys and one is the drops from the eyes. So when we are trying to do the word embeddings, these two word embeddings should be different, and accordingly the meaning of these two words should also be different. Okay. So let's start with the implementation now and try executing this code, and then we'll understand the complete code. This will definitely take a good amount of time because we want to install the two very important libraries, transformers and torch, because these two libraries would be used for the implementation of BERT. I'll share the slides also with you, and in fact the previous slides are also shared on the same Google Drive, which has been shared with you. It contains all the materials, and whatever the codes that we discuss is also shared there. So please execute this. I'll give you 5 minutes of time to do it. I'll again come back at 3:53. 5 minutes. Okay. So we have the encoder units, word piece tokens. That is, we are able to take out the tokens from the sentence. We did talk about the lemmatization, stemming, all that is done. Out of vocabulary words are taken into consideration. Then we go for embedding of these words. So embedding layer, either we go for a word to vec or a glove model. And when we are doing a glove model, then the representation, the context is also taken into picture. That is, a context should also be considered. And we have the different encoder units. Every encoder unit will have a linear layer before attention, then it will have a multi-head self attention, linear layer after the attention, and a feed forward neural network. And since we are talking about the transformer model, so it is parallel. So this is about the BERT base and the BERT large models. Base has 12 heads and large has 16. 24, sorry, large has 12. 24. So we have the mask language model and the next sentence prediction. So this is the, you can say, a gist of what we do. So input preparation, first and foremost, we add the CLS and the SAP tags in between. The input text is tokenized using the word piece tokenizer. Word piece tokenizer will take out all the words from the sentence, and it will add the tokens at the front and the separators. Tokens. Then we convert the tokens into IDs because we want to have a unique IDs with respect to which I would be able to identify the complete all the tokens. And whatever the steps we are looking at here, we'll actually do the implementation also there. And from the implementation, you would be able to relate whatever theory we have done with the code. So just see this theory quite well and understand the theory, because that will relate to the implementation also. Segment embeddings used to distinguish between sentence A and sentence B, and the positional embeddings. So as I said, the position of the different words. Then we have the embedding layer. And after the end of the embedding layer, I would be able to have this vector. Then I'll go for the transformer encoder layer. So first layer was input preparation, that is finding out the tokens and giving the token ID to them. Then it was embedding. And the third is a transformer layer. The transformer layer will have the attention mechanism, the addition and normalization, feed forward, and then addition and normalization again. It depends upon us whether we want to go for a base model or a large model. Once that is done, then the output representation For classification tasks, use the output corresponding to CLS token, and for token level tasks, use outputs of all the tokens. So in general, this is my flowchart. Tokenization, embeddings, transformer encoders, and the task specific layer. So the task specific layer will actually take care that what exactly you want to do with this BERT. You want to go for summarization, you want to go for recommendation system, you want to go for named entity recognition, whatsoever. And once it has been installed, then we can import it directly. Once the transformers are imported, then we would like to import the BERT tokenizer from the transformers library. So BERT tokenizer is a library inside the transformers, and which will help you to implement BERT. Now, from the transformers, I will import the BERT model, and this BERT model, I'm using a pre-trained model, which is BERT base uncased. BERT base means 12 layers only. So I'm choosing the base model of the BERT because I don't want to have a very large data set. So I'm fine with the BERT base model because base model in itself takes a lot of time. So just for the demonstration purpose, we are using only the BERT base model. HF token, I'm not sure whether you have been introduced to it or not, but let's see about the HF token also. The Hugging Face token. So I'll go with the user access tokens here. Have you used Hugging Face in any of the sessions earlier in this workshop?
No,
Did anyone huh? Yes?
not yet.
Not yet. Okay. So just go to Hugging Face. Log in with your Gmail credentials. It will ask you your Gmail credentials, so log in there. I'll wait here for some time. Logging into huggingface.co. Okay, I'm sharing the link for this as well. Log in with your Gmail credentials. Once you have been able to log in, it will ask you to create a token. You will have to find out where you can create a token. So you go to Hugging Face. Sorry. You can create new models here. You can create new data sets here, and that would be saved with your name. So you just click on this, go to usage quota, and there you will find access tokens. And you can just simply say create new token. Just write this in the name of the token. And simply just click create token. You should be able to see something like this. Once it is done, let me know.
Create new token, we can have to give an access or default thing.
Default, everything default. Just let me know once you are through. When you are able to create the token, let me know.
Yes, I'm done till here.
Okay, done till here. So now you can click on this and say you need to actually I hope you are using the same account with which you have logged in with Collab. So the Collab and this account should be the same. Once you have taken that, then you just click on this key which is mentioned here, secret keys, and write hf underscore token and give the value here. Whatever the value you can see here, just click, give it over there. Once your token would be created, you would be able to see that value. So write hf underscore token and give the value here. Click on keys and just say add new secret. Add new secret. So when I'm trying to upload this model, the BERT base uncased, then this model is given by Hugging Face. So you need to log into Hugging Face. So Hugging Face has given you a pass key to log into its platform. So this key is basically HF token is a Hugging Face token. So token is basically nothing but a key to log into its platform. Until and unless you log into the platform, you will not be able to access the different databases, different models which are available with Hugging Face. So you need to have this Hugging Face token. So token is nothing but a chabi, you say, the key to access its resources. Again, once it is done, let me know. So once you have been able to give the pass key, this will work. And if you see, it is able to upload the complete pre-trained model, and it has the CLS predictions bias, layer norm weights, etc., etc. So it is a pre-trained model. Now from this pre-trained model, I first had the BERT model, and then I'm having the BERT tokenizer. Both would be required, the BERT model and the BERT tokenizer, the pre-trained BERT tokenizer. I'm taking the same sentence which I had it in the slide. The little girl tears up everything she gets. She gets tears when she goes to school. So, as we discussed, these two tears are different. A different word embedding should be given for both these tiers. So first and foremost, I'm doing the tokenization. Tensors is equal to pt, return tension mask is equal to true. And I'm creating the input IDs, which are nothing but the token IDs, and I'm using the attention mask. Convert IDs to tokens. So basically what I'm trying to do is I'm trying to do the tokenization of the text. So if I just print the decoded text, the little girl tears up everything she gets. This is my actual text. And see, CLS and SEP have been added. SEP is end of the sentence and CLS is beginning of the sentence. What are the tokens? CLS, the little girl tears up everything and so on. And the token IDs are also given. So if you see here, yeah, to this is for CLS. 101 is CLS. The is 1996. Little is 2210. Girl is 2611. And 4000 is for tears. And the same 4000 has been given for tears, this one also. So both the tiers have been given same token IDs as of now, because currently I have not get into the context of the words. I have not taken any context of the words as of now. So the token ID would be same for both the tiers, both the she's. So this is tears up everything she. 2016 is she. So there are two she and two tiers, and both will have the same token ID. Check it out.
Yeah, madam, I missed one step where to insert the passkey that was generated from
Yeah,
Hugging Face.
just click on this secrets,
Okay.
and you would have add new secret.
Okay. Sure. Thanks.
So enter the name hf underscore token, hf underscore token,
Okay.
and then the key.
Sure. Thank you.
Okay, I'll wait here. I want each one of you to please do it with me, so I'll wait here.
Yeah, done till here. Thanks.
Okay, so you were able to do this part also. Can you just check it out? Okay, we have
Yes.
similar token for tiers
Yeah, it is coming same.
coming same. So what is the token that you are getting
For one
for tiers?
40 years, it's 4,000.
4000, same. Take it. The attention mask is 11111 because what we are doing it here is we are giving similar attention to all the words of the sentence. So what I'm trying to do is I'm giving equal importance to all the words of the sentence. So that is why here the attention mask is 1111. Now I say I want to find out the position IDs. So I'm using this command to give me the positional embeddings. So now if you just execute this code, it will be able to print. Can't extract, कहीं पे कुछ miss हुआ है लगता है. str to vec. It had executed earlier. If you could have seen, the output was coming. Not sure why. Tokenize it, dot convert. Acha. Yes. So now if you see this, it gives you the complete details. CLS is the token with the token ID of 101 decoded in this manner. And this is the positional embedding. Why do we need a positional embedding? Because with the help of this positional embedding, you would be able to have the position of each and every word with respect to other words. Okay, until and unless you have this, you will not be able to confirm the context, because as we have discussed, the tiers should have a different embedding. Both the tiers should have a different embedding, but how will it get that? Until and unless you are able to find out the position of each and every word, what is the position of this tiers with respect to the position of another tiers, what is the position of this tiers with the rest of the words, you need to do the analysis of the complete thing. So if you see here, we have added a asterisk in front of tiers so that you can relate this to two different. So if you see here, the positional embedding is different. This tiers has a different positional embedding with this tiers because we are considering the position of the word with respect to the other words of the sentence.
And the positional embedding vector is originally of the size length 786, correct?
It depends, yeah. Generally 786, but we are trying to print only the first five.
First five, yeah, yeah.
Yeah, that is what we are doing here. The first five, only first five. Okay. So the positional embeddings would be different. And now we are trying to do the positions and we are importing the cosine similarity for it. So the tiers positions were at 4 and 12. And these are the embeddings of the two tiers. So the first one starts with minus 1.02, second one, and the first one starts with minus 3.37. So if you see, the two embeddings are absolutely different. From where did I come to this point? After considering the positional embedding and also after building the model, because this is my model and I am giving all the inputs to the model. So I'm building the model here, the BERT model, which will find out the relationships of the different words in the sentence, including the positional embeddings also. The word embeddings, the positional embeddings, and the relationship with the other words. And if you see, the cosine similarity between tiers context is 0.71, 71%. And we can find out the difference between two words also. So if suppose I say Triple IT Nagpur is a centrally funded technical institute and sentence 2 yoga is a foundation of good health. Now these two sentences have nothing in common in between. So we are trying to find out the vector for technical and the vector for yoga. And then if you see the cosine similarity, it is 0.05. No similarity at all. It is 0.05, just 5% similarity between technical and yoga. And if you see here, so the cosine similarity between the vectors for bank is this, and for went is this. Because I went to the bank, I went to the river bank to withdraw, to take a bath, and I went to the bank to withdraw money. So these are simple sentences which I have taken myself. You can take whatever sentences you want and then try to figure out the difference between the two words. So the cosine similarity between vectors for bank is this and for went is this. So if you can see, both the banks are absolutely different. That is why the similarity is only 50%. Let me have a different set of sentence also. Will come in a minute. Give me the minute details of the project. So if you see here, the two minutes are different. The first one is we are talking about the time, and the second one is I'm talking about minute. So the spelling is same, the pronunciations are different, and the meanings are also absolutely different. So I say minute, minute. See, 46%. Same spelling, but still the words are different. And let's try doing it for same word with the same meaning also. Um, let's see if these two markets are same. Definitely, I won't get 100% accuracy, but it should be good enough. See, 96% same. How efficient it is. Try it out. I'll wait here for a minute. I want each one of you to try out different sentences, and whatever sentence you are trying out, just give me that in the chat box. Try it out and just put it on the chat box. What is the set of the sentences that you have tried? Similar meanings and not similar meanings, different pronunciations, different meanings, everything. Try it out and check how it is, how beautifully it is able to differentiate between the different words used in different contexts. I hope you have tried the different sentences. Can you just put on the chat box what are the sentences that you have tried? Different words, like you can check it out for bear. I saw a bear in the jungle today. I went barefoot to the temple. Same pronunciation, same spelling, but different meanings. Very similar to bank. See, 39% only. And let me try it out. Same pronunciations, different spellings. Same pronunciations and different spellings. This was actually, oh sorry, this will have a different spelling. Yeah, different spelling. और कम हो गया, 39 से 26 रह गया, because now we have a different spelling also. So what are the different things that we have checked? Let me write it down here. Same spelling, same pronunciation, different meaning. है ना? Here what we have done, same spelling, different pronunciation, different meaning. And what we have done here, different spelling, same same spelling, same pronunciation, same meaning. So we are getting a similarity of 96%. Such a huge similarity. Check it out, different sentences. So this will actually give you a feel that how the system is able to understand different sentences, how it is able to understand the meaning of the sentence. So we have checked it out for different pronunciations, different spellings, same spellings, all the permutations, combinations we have done. And here there was no connection at all. Absolutely two different words in two different contexts. No relation at all. See, if there is no relation at all, it is 5%. Slight relation, 56%, 46%, 26%, and 96% same words, absolutely same words. Then let's see another application of BERT for sequence class for question answering. We'll do it for question answering. So just let me know once you are through. I have not received any sentences in the chat box, which I am waiting for. Okay,
I want
Abhinav sir
posted.
mentioned. Yeah, Abhinav said a bank runs on trust of its customers. He runs daily in the morning. Acha, so you are going for runs? 51%. Very good. So one is bank is, the runs here is working. In the second sentence, runs means working. And in the first sentence, runs means actually running. So the two runs are different. So that is why you are getting a similarity of 51%. 52. Fair enough. And what about other? What about others? Pragati ma'am, others? Jyoti, Janice. Okay. So you don't have the resources. Ravi sir, you are not implementing it on a laptop? Because you just need a laptop. Collab will work. You don't have to install anything for it. For projects, acha. Lavanya ma'am deposited money in the bank. The fisherman sat on the bank of the river. So the two banks has 42% accurate, 42% similarity. Very good. The vectors for projects is 43% and for features is this. Okay. So Jane, what were the sentences that you used?
Ma'am, I have given in the previous chat.
Okay. Acha, got it. Yes. This projects the features of the goods. I'm doing a few projects with similar features. Okay. So the features was same. So you got it 49%. For features, you should have got even more.
A feature is same meaning, ma'am.
Half the features are same meaning, no, but still you are getting only 49%. So you should have gone more because here actually yes, features is slightly confusing because in the first case you are talking about the features of projects, and second case you are talking about the features of the goods. So that is why you got 50%. If the features would have been same for both the people for both the things, like the features of goods in both the cases, you could have got a better similarity. Got the point?
Okay. Okay, ma'am.
है ना? In the first
Got
case,
it.
you are talking about the features of the projects, and in the second case, you're talking about the features of the goods.
Okay. I
So
got
that
it, ma'am.
is
If
why,
the
yeah,
sentence is slightly different, I will get better results. That's it.
yes. So if you say features of goods in both the cases, you will get more than 90% in that case.
Okay.
Similarity, as I showed you, no, that is if you are using market in a similar manner, you will get 96% accuracy.
Okay.
Sorry, accuracy, nahi, similarity. 96% similarity. Okay. So let
Okay.
next do the question answering. We are using BERT for question answering, and so pipeline is a function which takes care of the complete thing. You don't have to mention anything here. Just why do you want? What do you want to have? I want to do the question answering, and what is the model that I am using? So BERT, large, uncased, whole word, masking, fine tuned, squared. So this model is actually present with Hugging Face. So I didn't want to do anything extra on this. I just wanted to use a model which is already present with Hugging Face. And I simply give the question and the answer. So this is the context. Context means a paragraph, on the basis on which I would be asking the question. So I simply said Triple IT Nagpur was formed in 2016, etc., etc. And when was Triple IT Nagpur formed? I'm just asking a question from the paragraph. So let's see if it is able to give me the answer as 2016. It will implement the complete, it will complete model on this paragraph, on this data in this corpus. If the corpus is more, the data is more, then it will take even more time to do it. Answer to the question is, answer is 2016, and it is 98% scoring. 98% score means it is 98% sure that the answer is 2016. So it is giving the answer with 98% accuracy, and that's absolutely correct. It is very clear that okay, it was formed in 2016. In this case, what I'm doing, I'm saying that okay, you give the context, you give the question, and I'll answer the question. So let's say I'll give the context. India winning T20 World Cup. I hope most of you saw the match. It was a wonderful match, in fact, a treat to the eyes. So let's take this as the context. Okay, and what are the things? India have now won the title for the third time. So how many times India has won? You know, I'll just simply give the question like this. How many times India has won the title? See, third time. Why is it giving 19% accuracy? Because here I am right giving the question in an indirect way. I have not given a direct question. Which that is this the second time that India is winning? So then it may have answered the question, no, it is the third time, and it would have been with a better accuracy. So how many times it has run is something different from the context, because context said if type for the third time after so and so. Try it out. And in the third thing, what I have done is, okay, I'm saying that if the score is less than 0.5, you simply say you don't know the answer. Don't give me a wrong answer for it. Okay, na? So suppose if I say please enter the question, I give the question as from where you have done the PhD. Now this question I have not answered in the context. I don't know the answer. Simple. Where do you work? See, it is 57% sure that you are working in the Department of Computer Science and Engineering. So if the answer what you are getting from the system, the system is more than 50% sure, then only it will give the answer. Otherwise it will simply say I don't know the answer. I don't want any questions. And that is the biggest problem of large language models. I don't want a wrong answer. Try it out. And this is question answering with a this was which model it was using. This was the model of BERT large uncased whole word masking fine tuned squad. And this is also BERT large uncased whole word masking fine tuned squad. That's it. So just try giving different contexts, different questions, and check whether you are getting the correct answers or not. And this is a very nice exercise which actually tells that how BERT works. So at the very first instance, if you see, we just saw we had the same sentence in the slides, and we checked that how exactly it works. So this is the complete breakup of how it is getting implemented. I'll share the slides with you at the end of the session, and this can be checked at the same Google Drive where all the material is being. So the difference between BERT and GPT, as we already discussed, is that in the case of the GPT, it is only a decoder model, but BERT is an encoder model. So it's designed for generative language modeling. It predicts the next word in the sentence. So it basically GPT is being used in the case of the chat GPT thing, in which we are predicting the next word again and again and again. And BERT is used to predict the missing words in the context. It is using the mass language model objective and to predict the next word in GPT, which encourages the model to learn a coherent representation of language and generate contextually relevant sequences. So BERT is basically used in those tasks in which a deep understanding is required. So that is why the encoding is must in those cases. And in the case of the GPT, we do not need to encode the query. We just need to generate new text. So that is why decoding is important in that case. We are creating new things. We are creating new text. We are creating new images. So in that case, decoding is more important as compared to encoding. And BERT is used in those applications where we need to analyze the input and accordingly give you the desired output. So in text classifications, in NERs, and sentiment analysis and question answering, we use BERT. We don't use GPTs in cases. So wherever we are generating something new, we use GPT. And whenever we want to analyze the input, we go for BERT. The encoding. Okay. So I would be sharing these slides along with the code that I have just discussed. This code. Any doubts, any questions? I hope you are able to execute this code completely with HF token. Good for now. Great. Sir, you were sending a mail. I didn't receive any mail from your side. You had said that you would be sending a mail.
I already shared it, I think, today, just before this session.
I didn't receive it.
Okay, I'll share
Just
it
before
again.
the session. Just give me a second. If I missed it.
I'll check my outbox as well. Yeah.
No, I haven't received any mail. Acha, acha, acha. Okay, this one. Yes, 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 yes. Oh, I thought this is of some student, so I missed it. Okay, I'll go through it.
Sure. Thanks.
Because nowadays we are getting a lot of requests for summer internship by the students. So that is why I missed it.
Actually, that is also a Yahoo ID, probably a bit old. So
No, even I use Yahoo ID. I always use Yahoo ID instead. Well, official is Gmail, but I use Yahoo as my personal email ID.
that is good.
So thank you so much for joining the session, and I hope it was a useful and an interesting one. I like actually a lot in this case. You can relate the theory to the practical. So whatever we say that okay, BERT is doing this, BERT is doing this, then we can actually see what exactly BERT is doing and how it is doing. What are the outputs that we are getting in each and every phase of BERT can be very well seen at the time of coding. So I really love this program a lot. Whatever we said that okay, context is important, the reference is important, and then we are trying to figure out the relationship between the different words. All this is actually visible in the code itself. So now you would be able to relate well. Whatever we are studying in the theory is not just theory, but we can actually see it happening in the code. So thank you so much once again. I am sharing my email ID. Again, if somebody else wants to get in touch, and if you have any doubts or questions, you can shoot a mail to me. Thank you so much. Take care. Have a lovely workshop ahead. Thank you, Christy.